Good morning, guys. Um, Good morning once again. This is our third unit. I hope you had a good weekend. And this third unit is called complex numbers. Now, a brief history of complex numbers. So back in the day, because we all know that, what am I even saying? Back in the day, mathematicians were trying to figure out how to go beyond problems where they encountered the square root of a negative number. Because if you look at all the real numbers in a number line, uh, and so on, all the real numbers in a number line, all of these numbers obey this function that f of x is equal to x squared. So if I get any input from any of these numbers in the number line and put it in this function, they obey it, all those real numbers. However, all those numbers do not obey this function, f of x is equal to the square root of x. So all the numbers from 0 onwards on the positive side of the number line will obey the function of the square root. But all the numbers on this side of the number line do not obey the second function, which is square root of x. And mathematicians struggled for a long time because every time they came across a problem where they encountered the square root of a negative number, that problem ended there. They wouldn't be able to find a solution because the square root of a negative number, as we all know, is undefined or impossible or, etc. Until some Italian mathematician, whose name I've forgotten, came up and suggested that what if we introduce this imaginary number called I, right? And this imaginary number called I would stand for the square root of -1. So I is basically the square root of -1. So every time you encounter a math problem that involves taking the square root of a negative number, then that number can be represented by the letter I. So on this number line where you have squares, because on this side, if I want to have squares, on this side, if I take square roots of all of the numbers on that side, they will give me a real number. They will give me a real number, which is a natural number. But if I try to take the square root of all the numbers on this side of the number line, then if I am not using I won't get anything. But if I use I, which stands for imaginary numbers, then I will have, on this side of the number line, I will have imaginary numbers. So that's the basic idea behind complex numbers. A complex number is a number that has two parts. One part is real and one part is imaginary. You can watch the TED Ed video that I posted to get a little bit of more history and fun, interesting facts about these imaginary numbers. Now you could be wondering, why are we even studying these imaginary numbers? How are they helpful? Well, in the world today, in the world of engineering, in the world of physics, a lot of the problems that we do in school do not take into account things like air resistance, right? Air resistance is not taken into account. Sometimes they only deal with constant acceleration, and the physics people will tell you that this is true. Most of the physics problems deal with constant acceleration. They don't take into account some other factors, but if it's impossible to create a model, it's impossible to create a car suspension system, it's impossible to create a suspension bridge, a plane, a parachute, or any of these things that can be life-saving or useful to humans if we are not considering the factors that affect everyday life, like air resistance, like friction, like wear and tear, like damping of oscillations. So if we consider each of these things, then the equations that we use have to include certain things a lot of the time, which will fall in the realm of imaginary numbers. So these numbers are very useful in the field of engineering, are very useful in the field of design of models. So that's a brief introduction. Just remember, I is the square root of -1. That is the key idea for today. I is the square root of -1. We're going to look at how we can perform basic mathematics operations on complex numbers. Yeah, and etc. So if I is the square root of negative 1, then this is just square root negative 1. This would be square root of negative 1 times square root of negative 1, which, if you remember, is just negative 1, because the square root of a number squared is that number. The square root of 2 squared is 2. So yeah, I hope you remember that. I hope you don't get confused and want to multiply the negative by the negative to get a positive, because it's not the negatives that are multiplying, it's the square root of that number multiplied by the square root of that number again, so the square function cancels out. Now, I to the third power, I already know what I to the second power is, and I already know what I to the first power is. So I can write this as I to the second times I to the first power, which I know I to the second is negative 1, and I to the first power is just I. So, well, the task here is to try and express these numbers as simply as possible in terms of I. I hope, yeah, that's the task. So this would just be negative I, right? I to the fourth power, I can write it as I to the third times I to the third times I, or I can say it's I to the second times I to the second. If I use I to the third power, then that will be negative I times I, which will give me another job of trying to simplify that. Or if I use I to the second power, it will just be negative 1 times negative 1, which, looking at this, I know that the answer is positive 1. But also looking at this, you can see that we know I times I squared, which is negative 1, but there's already a negative in front of it, so that will still be 1. So I'm going to give you an extra credit opportunity or a task. I need you to find before we get there, let's first simplify this. Before we get to the extra credit opportunity, it's coming up in the next slide. I'd forgotten the order of this slide, this slide. So I to the 35, try to break it down into the powers of I that you know. For example, 35 I know is the same as, if I want to get I to the 35, what numbers am I going to multiply to get I to the 35? That's going to be 7 times 5, right? I can write this as I to the 7 times I to the 5, right? So I need to find what I to the 7 is. I know that I to the 7 is I times 7 times 3, 4, 5, 6, 7. And I to the 5, same thing. I 5 times 1, 2, 3, 4, 5. So, I to the 7 can also be written as I. Wait, what am I doing? Sorry, this is not true. This is so not true. Ignoring the rules of exponents. So, I to the 30, remember, if I am multiplying exponents, then I'm adding the powers. So I can write I to the 30 as I 30 times I 5, right? Or, so you're going to try to find a way to break it down as much as possible so that it turns into something that you know. So again, this would have helped if I already knew what I to the 6th power is. So I'm going to go back here and figure out what I to the 6th power is. So I try to figure out I to the 6th power. That can be I to the 4 times I to the 2nd power. And I know I to the 4th power is 1, and I to the 2nd power is negative 1. So I know I to the 6th power is negative 1. I don't know if you see a pattern. You can let me know if you see a pattern. There doesn't necessarily have to be one. But if you find a pattern that will work for you, cool. So I to the 6 is negative 1. And to solve this, I'm going to use the idea that I to the power 30 is basically I to the power 6 multiplied 5 times. So if I have I to the 6 times I to the 6 times I to the 6 times I to the 6, how many others? 1, 2, 3, 4 times I to the 6. Because I'm multiplying, I'll just add up the powers. and adding up the powers gives me 30. I know I to the 6th power is negative 1. So I'll have negative 1 times negative 1 times negative 1 times negative 1 times 2, 3, 4 times negative 1, or simply negative 1 to the power of 5, which is negative 1. I to the 68th power, you're going to do the same thing. Try to figure out a way to break it down into powers that you already know. So it's going to help if you're going in order, powers that you already know, and then after you do that, you can find the I to the 60th power. So I could personally say this is I to the 60 times I to the 8, and I can break 8 into 4 times 4 because I already know what 4 is. I can break 60 into 10 sixes. I can say this is I to the power of 6 10 times to the power of 10 because it's 6 happening 10 times. So I to the power of 6 is negative 1, that is power of 10. I to the power of 4 is positive 1, that is happening twice. So negative 1 power 10 is 1, and positive 1 power 2 is 1. So I end up with 1. I hope this helps. Wait, did I make a mistake on this previous one? I to the 35. So 1, 2, 3, 4, 5. These 4 give me, yeah, I think we're fine. Right? No, that was just 30. Apologies, that was just 30. And then multiply everything by I to the 5th power. I knew that this was wrong because the pattern that I was asking you for, so I have to multiply my answer with I to the 5th power, which I to the 5th power, if I to the 4th power is 1, I to the 5th power will just be I to the 4th times I, which is 1 times I, which is I. So I to the 4th, where am I? I to the 5th power, which is this one times I, so my answer is negative I. The only reason that I was able to check this is because I know that the pattern I was asking you for is that even numbers always have a real number expression. Even powers of I have a real number expression, and odd powers of I have an imaginary number expression. So you can also try to find that when you do your work. I to the 21st power, this is I to the power 20 times I to the power 1. Now I to the power 20 is the same as I to the power 5 4 times I to the power 1. I to the power 5, I hope you guys remember, was, do you remember? I can say it's I to the power 5 4 times, or I can say I to the power 4 5 times, right? I to the power 4 5 times would be easier for me, times I, because I know I to the power 4 is 1, power 5 times I, so my final answer here is I. Again, odd number, it has an imaginary number expression for the power of I. I to the 42, I can say this is I to the power 40 times I to the power of 2. I to the power of 40 is I to the power of 4 10 times I to the power of 2, which I know to be negative 1. I to the power of 4 is 1 10 times negative 1, which is final answer is negative 1. Even power of I has a real number value for the expression. So I told you about before that the imaginary number is the square root of negative 1, and a complex number is a number in the form a plus bi, where a is the real part of the imaginary number, of the complex number, and bi is the imaginary part of the complex number. So this is the extra credit I was telling you about. You're going to get 5 points on your next test if you can figure out the powers of I from Just pick 50 of the numbers from 1 to 100. So you can start at I1, I2, I3, I4, all the way to 100, but just pick out 50 numbers. So my suggestion here is that you do the odd powers from 1 to 50 and the even powers from 51 to 100. If you have that done before the end of the day tomorrow, not today, you get your extra credit. Good luck. I need you to show your work on your paper. I need you to show your work breaking it down in the ways you broke it down, because I know you can just use a calculator to solve for this, so I don't want to be cheated. So we can do arithmetic operations on complex numbers, including addition, subtraction, multiplication, and division. When I'm adding complex numbers, then I just need to add the real, it's like collecting like terms. I need to add the real parts together, and then I need to add the imaginary parts together. So if these are my two complex numbers, the real parts are A and C, which are in blue. I add them together, they form one number. And then the imaginary parts are B and D. I add them together, they form another number. And all together, those four terms form one complex number. When I'm subtracting complex numbers, it's the same thing. I subtract the real parts, and then I subtract the imaginary parts. You guys need to write the actual answer. It's just a symbol. Some examples, if I want to perform the operations indicated. So here, the real part is 3 and 2. I'm going to add, because the operation in the middle is addition. I'm going to add 3 plus 2. And then I'm also going to add negative 4i plus 5i. So 3 plus 2 is 5, and negative 4i plus 5i is just I. So my new complex number is 5 plus I. Here, the operation is subtraction. I'm going to subtract 3 minus 2, and then I will add the subtraction of negative 4 plus, and then I'm going to add negative 4i minus 5i, right? 3 minus 2 is 1. Negative 4i minus 5i is negative 9i. I know you might be wondering, why did you put addition here? Because it's subtraction, blah, blah, blah. The idea is I am trying to work this out. First of all, what you could have done would have been to take out the parentheses. Minus 2 minus 5i. And then at that point, you can go ahead and say this is 3 minus 2 minus 4i minus 5i, which turns out to be the same thing. So yeah, I did that because it turns out to be the same thing, but if you want, you can go ahead and take out the parentheses and do it at a slower pace. Find the indicated operation and express the result as a simplified complex number. The square root of negative 9, I know negative 9 is the same as negative 3 squared. Negative 3 squared is the same as negative 1 times 3 squared. If I use the rules of the radical, I can split this into negative 1 times square root of 3 squared. I hope you can see that the square root of negative 1 is I, and the square root of 3 squared is 3. So my final answer is simply 3i. Negative 4, so just by looking at this, I know the square root of 2 is, the square root of 4 is 2, and the square root of negative 1 is I, so that's just going to be 2i, following what I've done earlier in that example. And this one, I might need to write this one out, because the square root of 8, if I write that one out for you guys to see, it's the same as 4 times 2. 8 is the same as 4 times 2. So this will still be I, because the square root of negative 1 is I, times the square root of 4 times 2. So this is 2i times I times the square root of 4 times 2. 4 has a square root, but 2 doesn't have a square root. So this becomes 2 root 2. This is what I was trying to show you. So 2i times I is 2i squared, which is negative 2. And then this negative 1 is also I, so I have an I right there. So I have 3 i's, which I now turn into negative I, and then I have 2 times 2, which is 4 root 2 I, but it's all negative. Yeah? Okay, work out this. Negative 4 into 2 plus 6i. I just need to work this out like it's a normal FOIL. Negative 4 times 2 is negative 8. Negative 4 times 6 is negative 24i. Same thing here. I'm just going to use FOIL to work this out. So 4 plus 3i and 2 minus 5i is 4 into 2 minus 5i plus 3i into 2 minus 5i. Simplifying gives 8 minus 20i plus 6i minus 15i. So I have 8 minus 20i, sorry, this would be 15i squared, because 3i times 5i is 15 times I, which is I squared. 8 minus 14i minus 15i squared is the same as negative 1, so this is negative 15. So 8 minus 14i plus 15. 8 plus 15 is 23 minus 14i. That is my new complex number. Okay, you guys do this for your homework. Bye.